In this video I want to talk about Dalton's Law. This should be a review from pre-AP. If you're in pre-AP watching this, this will also give you a good overview of how to use Dalton's Law. The very first thing you see here is a picture, and this illustration is critical, I think, for you to understand what Dalton's Law is all about. In the first little cylinder here, you have one gas represented by the bouncing blue balls. And you can see that there's a pressure created by each of these balls striking the walls of the container. That's what creates pressure in any gas. And then you can see in the second cylinder you have a different gas represented by the color orange doing the same thing. Well, what happens if we put these two together and mix them to make a homogeneous gas mixture? You can see from the way this picture overlays is that they continue on their merry way with nearly the same velocities, the same number of collisions per gas molecule. So they just add together. Each of the pressures just adds together. So the total pressure in this cylinder would be equal to the pressure of the blue gas plus the pressure of the orange gas. That's a very simple concept when you deal with Dalton's Law. Pressures of the gases are just additive. Let's just briefly review some of the kinetic theory aspects and the theory behind Dalton's Law. So kind of the main idea here is one of the gases. We don't really have a relationship that we talked about with the other basic gas laws like Boyle's and Charles and Avogadro's and Gay-Lussac. But this is just another one of those proportions, this time dealing with P and N. It just simply says pressure and moles are directly proportional. You know that. If you keep blowing air into an inflatable raft or a tire or a beach ball or whatever, you keep adding air in, it becomes tighter, more pressure as you put more molecules in there. The thing that's kind of different about this relationship is that additive aspect of it, where it also works for mixtures of gases as well. But it's other than that, it's just a simple another proportion to add to our list. The second bullet is your key to understanding how mixtures work. Each gas creates its own pressure independently from its own collisions with the walls of the container. The next bullet is just a summary of how to. It's the most basic application of Dalton's Law, when you just add different pressures together to get a total pressure, and that's what this little T right here stands for, total. And it could be for any number of gases. It could be up to, infinite number of gases being added together. And the fourth bullet is interesting because they are directly proportional. The mole fraction equals the pressure fraction. So let's just say here that half of the moles in my balloon are helium and the other half are hydrogen. Well, my pressure is also going to be half due to the hydrogen and half due to the helium. So whatever fraction of moles you have is the same fraction that's going to contribute to your total pressure. Now let's run through just 4 simple examples of the different types of Dalton's Law problems you may see. It may not be an inclusive example list, but this will get you through most everything. So you see here we have a mixture of hydrogen and helium. It's a mass of each right now. And we have the containers. Alright, so let's go ahead and do the most obvious thing here, and that's convert each of these grams into moles. Alright, so for hydrogen that's going to be H2, so it's 2 grams, and for helium it's going to be 4 grams. It comes out to be 0.500 moles of hydrogen and 0.25 moles of helium. Alright, now there's 2 ways to work this problem. Because it wants to find the partial pressure of each gas and the total pressure. So the way I'm going to work it this time, in order to get the partial pressures first, is I'm going to use the ideal gas law. And this is another interesting thing here. We've learned PV NRT in pre-AP, and you guys are pretty comfortable with it. But what we didn't tell you when we first started ideal gas law was that we're assuming it's either a single gas, but if it's a mixture, we were always finding the total pressure, the total moles. But we can also apply the ideal gas law to apply just to a single species in a mixture. So for example, if I want to find the partial pressure of hydrogen, I'm going to use PIV-NERT, but instead of total moles, I'm going to use just the moles that I have of hydrogen. Everything else stays the same. Volume is the same, temperature is the same, all that good stuff. So let's do that. Partial pressure of hydrogen equals, I'm just plugging it into the rearranged form of the ideal gas law here. I'll show you how I rearranged it one time, then for helium I'll just show the work. Alright, so plugging this in here for hydrogen, 0.5. I'm not going to show my units to save space here, but this is 0.0821 liter atmospheres per mole K for R. And then the temperature here is 27 Celsius. Remember, we have to be in Kelvin, so that's 300 Kelvin with 3 sig figs. And the volume is a nice 1 liter. So that gives me a partial pressure of hydrogen to be 12.3 atmospheres. Okay. Let's do the same thing for helium. And instead of 0.5, our moles are 0.25. R is the same. Temperature is the same. And volume is the same. So this will give me a number here, 6.16 atmospheres. So that's the partial pressure of each gas. So now the total pressure, we're just going to add those two up. So it'll be 12.3 plus 6.16. And I got 18.5, rounding it to sig figs. So main idea of this example problem is you can use PIV-NERT for partial pressures in a mixture if you just use the moles of that particular species. This next one is a problem that the AP test loves to use nowadays because it shows proportion. And most students look at this and kind of freak out a little bit because they see a picture and you don't understand what's going on. It says we're going to open up the stopcocks, which are these things here, valves, and these gases are going to mix. Well, what changes when these gases mix? The most obvious thing that's going to change is volume. And the volume will just be additive. So we add these up, and each of these gases are going to fill afterwards 4 liters independently. So really all we have to do is we can use Boyle's law here, and we can find the ratio of change. Like what's going to happen, what's V2 going to be for helium, what's V2 going to be for neon, and then what's V2 going to be for argon. And once we have those partial pressures, we can just add them together. The only other little trick to this problem before we get started is that we need to be in the same units of pressure. So I'm doing a pressure conversion. Just remember that 1 atmosphere is 760 torr, and that also 1 atmosphere is 101.3 kilopascals. Those are conversion factors. To save time, I'm just going to give you those conversions already. The first one I'm going to leave in torr. For this one, I'm going to make P1 be not 0.4 atmospheres, but converted to torr, 304 torr. And then for argon, I'm going to convert it. P1 is equal to 180 torr. Alright, so now I'm in the same unit. So let's do the work for each gas. Let's do helium first. And again, we're doing Boyle's law. P2, V2. to plug this in, we're starting out at 200 torr. Again, I'm gonna drop my units off to save me a little time and space here. We're at 1 liter. Let's figure out what that P2 is going to be when we go to 4 liters. P2 for helium comes out to be 50 torr. Okay, let's do the same thing for the neon. We still have 1 liter. The pressure this time starts at 304. Still going to change it to 4 liters, and what will the pressure be? We do the math here. 304 divided by 4, we get 76 torr. And for argon, this time we have 2 liters with 180 torr. And then we're going to change that into 4 liters. And I got 90 torr for that one. So those are the partial pressures. Now to find the total pressure, we just add those 3 answers up. Comes out to be 216 torr. So really not a very difficult problem at all once you get past the initial panic of, oh my gosh, this is a weird picture, what am I supposed to do? Remember, each gas is independent in a mixture. Okay, next we have a more wordy problem. It looks like a long problem's coming up, but it really isn't. It stays pretty simple. Well, this time we have a mixture of methane, CH4, and oxygen, and we're given partial pressures of each. So to find the total pressure here, I'm just going to add up the partial pressures. Here's methane, here's oxygen, so let's add them up. 0.175 plus 0.25 to get 0.425 atmospheres. Alright, part 1. What is the mole fraction of each gas? Well, mole fraction is just any fraction is just a part over the whole. From pre-AP, when we use the capital X, it's really a chi from the Greek alphabet, but it looks like an X, so let's don't overcomplicate it. Let's just say X. Okay, so the mole fraction is going to be the moles, the part, in this case, of methane, so that's 0.175 over 0.425, which is the whole thing. And that fraction comes out to be 0.41. Now, you may be thinking to yourself, whoa, 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 what are you doing? You're looking for a mole fraction, but Mr. Taylor, you used pressure numbers. How can you do that? Well, remember back to our second slide, the 4th bullet. The mole fraction of a gas is equal to the pressure fraction of a gas because P and N are directly proportional. So I can do this. This is perfectly fine. And it saves a heck of a lot of work. So now let's find the mole fraction for oxygen. It is 0.250, that's its part over the whole thing, and comes out to be 0.59. Units, no units. Part B, we're given a volume now and a temperature. This temperature, if you add it, turn it to Kelvin, is 338 Kelvin. So we can get that out of the way. Calculate the total number of moles. All right, again, we can use pivnert, but if we want a total number of moles, this is NT. So I have to have PT. So as I'm doing pivnert, I'm just aware that this is PV with total pressure equals nRT with total moles. And we've got all that information, so we're in good shape. So just plug it in here. We've got 0.425 atmospheres. Again, I'm going to hold off on my units to save space. The volume is 10.5. Looking for that NT. I'm in atmospheres, so I can go ahead and use 0.0821. And we've got that temperature already lined up. Simplifying for NT, I'm not going to insult you with the algebra. You can plug it into your calculator, make sure you get the right answer. If you want to hit pause, that's fine. but total moles is 0.161 moles. And then finally, the number of grams of each answer, or for each gas. I want to go back to that mole fraction now. The moles of methane is going to equal that mole fraction times the total number of moles. I'm using that pressure fraction, mole fraction interchangeably here. And if I plug in those numbers, going back to part A, it's 0.41 for methane. And the total moles, if you go to part B, 0.161. So that gives me 0.0656 moles of methane. And then we'll convert that to grams by multiplying times the molar mass, 16.0 grams per mole. And I got 1.05 grams. All right, now you do the same thing for oxygen. Hit pause, do your calculations. I'm going to give the answer at the top of the page here in a second. All right, let's check your work. You should have gotten for the moles of oxygen 0.095, and then multiplying by 32, 3.04 grams of O2. So that last problem really wasn't as long as it looked. Here's another one. This type of problem falls, of course, in the gas law curriculum, if you will, the content, but it also reaches over into lab. And there's a lab question every year on the AP test. Let me describe briefly what you see in this picture because it has to do with a lab technique called collecting gases over water. Here in the test tube, we have a reaction, zinc and acid. You've all seen this reaction in pre-AP. Hydrogen gas, a single replacement, so hydrogen gas you can see being bubbled up here. Well, think about that. If we were doing this in a beaker, the hydrogen gas is made and it just floats away. So collecting gas is a very difficult, well, not difficult, it's a very tedious thing in chemistry because we have to have an apparatus or some way of collecting a gas without it floating away. So we can use water because gas is less dense than water. We just run a tube through the gas, or through the water I should say, and the gas bubbles up inside of a container here, a bottle, it could be something called a eudiometer, which looks like a giant burette turned upside down. Anything. And the gas will just simply float. It'll fill this headspace up and create a pressure inside of there. And that's it. The only tricky thing is now this becomes a mixture. Because any gas you collect over water is going to include the gas. I'll tell you what, in this example it's hydrogen. But it will also include water vapor that evaporates from the surface of the water. So you automatically make a mixture. So in this lab technique, you have to understand how to use Dalton's law to get that water vapor out of your calculation, or it will be wrong. So in this particular problem, we have hydrogen being created, and we can see they're giving us the partial pressure of the water. You may be wondering to yourself, how am I supposed to know what the partial pressure of water is? Well, that's a good question, actually. The most important information here to know that would be the temperature. Once you know the temperature you're collecting the gas over water, you can go to a table in any kind of like chemistry handbook or chemistry appendix, and you can usually find a table that says, okay, at 25 degrees, water has this certain vapor pressure, and you just look it up. So at this temperature is 23.8 torr. What we have to do to start off with this helium is get it out of grams and into moles. Let's do that real quickly. It's 1 mole over 4 grams. So that'll give us 0.1465. I'm including some extra sig figs here. And that's going to be moles of the helium collected. And I know in my picture I have hydrogen, but the problem is dealing with helium, so don't be confused by that. I just found a picture online. All right, so it says we have 1 atmosphere of pressure. Just remember that equals 760 torr. So the partial pressure of helium in this particular problem is not 760 torr, it's going to be 760 torr minus 23.8, which is because of the water. So the pressure, yeah, it is the partial pressure of the helium here, is 736.2 torr. And now if you want to find the volume, it's just piv inert. I'm rearranging piv inert here, so this will be nRT over P. And we just sub in these numbers. I've got the moles, 0.1465. I'm in torr this time, so I do need R and torr. You can look this up if you don't believe me, but R and torr is 62.4. We've used that value before. And 298 Kelvin, that's 25 Celsius, over that pressure that we just calculated. And so ultimately, the volume of this helium comes out to be 3.70 liters. So again, nothing too earth-shattering here. We just had to understand that this is a mixture because of the way it's being collected. We calculate using Dalton's law to get that water out of there, and then we're back to our very familiar piv inert. All right, try those practice problems on your own. If you have any questions, come see me.